So Fluent kind of has a new UI. Anyone looking at these slides that use Discovery will immediately say, hey, that looks pretty familiar. Ansys, I think, are going towards this theme that's based on how Discovery currently looks for lots of their products at the moment. The good thing about this is that it takes like all of the local rendering and interaction of Fluent and puts it in a browser. So if you've got like a headless Linux node sitting somewhere in a cabinet that you don't have a display for, it doesn't have a GPU, so you can't do any the remote desktop experience is crap, right? What this lets you do is essentially run Fluent as a server, and this will interface with it through a web browser, and you'll be able to render things locally. So we'll have a look at this in a sec. The other really good thing about it is because it's slightly like less of a live process, I've actually found that it's a bit snappier than running the Fluent GUI natively. Again, if there's Fluent, of the Fluent users in the room will probably know what I'm talking about, where sometimes you click on something in Fluent, and it might take a couple of seconds until you can sort of interact with it, particularly like little boxes where you want to enter a value. Sometimes you click in them and you just have to wait a second to be able to type. The web UI is a bit snappier in that regard. I'll show a demo on that in 1 second, just after this slide. This the last thing here on the sort of UI side of things is that Fluent now has access to 2 of the optimization methods that are from OptiSlang. So if you are wanting to use one-click optimization or an AMOP, rather than firing up OptiSlang and putting Fluent in there and running it that way, Fluent itself on the parametric tab has access to those OptiSlang algorithms. So you can do the whole project just within Fluent itself. Cool, let's just have a really quick look here at the web UI. I'm just gonna see how I'm doing for time. Not too bad. All right, so we'll come back to that BOF one in a sec. I've got a second Fluent case open here. And you'll see that there's nothing too interesting. But when I launched it, you'll see that it's sort of said it's got a web server started here. So I'm just going to very quickly show you how I did that. I'm not going to do the full launch. I'm just going to show you where it is. So on the general options tab, you'll see that there's a start web server button down here. And you give it a token, which is just a password to access that session. So that's all I've done. I've clicked that, I've put in a token, and I've launched Fluent. Then what I can do is in my web browser, I can go to the port that was specified there, which is 5000, and connect to it. Now, this is just obviously running all on my laptop, so I've just written localhost in there, but if that was a server sitting in a cabinet, I'd use the IP address of that server. So here we are. It looks pretty familiar, right? It's pretty much the same as the left-hand side in regular Fluent. So I can go in here and sort of look at my inlet boundary. I can change some values in here. Do that real quickly. I don't have to hit apply. It's kind of like a live process. You change a number and it will write that back into the solver. I can maybe go in here and show a contour. Or I could make my own new contour. Now, you'll see that I did just make that change, right, to the velocity inlet. I changed it from 20 to 10. If I now go back into this session here, that change should be reflected. Yeah, that now reads 10. You don't have to do this with the graphical session, by the way. I'm just showing how they're linked. So if I was to just run this real quickly, actually, I'll make a new object. I'm going to go and make a report definition for pressure at the inlet, maybe. Grab that, static pressure. And now I'll make a report plot for it as well. Just grab that. And I'll hit run. And over here, can view my, it had already, I read in a case and data that was already solved, but obviously I've changed the inlet velocity there. So we're seeing that represented. And I can go down here and I can ask for 2 tiles. And now I can see that report plot that I just made as well. I can change the layout of that. So it's a really nice sort of flexible environment. And one other thing that I found is, while this is solving, I can still kind of do things. Like, I might be pushing my luck here, to be honest, but I could come in and make another contour. I don't know, maybe just go static pressure on the inlet and save and display that. And whoop, there it is, right? So even while the case is still running, I've got way more access to the code than usually in like the Fluent environment over here. There's no way that I could have just made that that contour while it was running. Just one last thing on the web UI, and this is going to play into our last demo, but I just want to show you that we've got a new console in here. So we've got this Python console, and every time that I've clicked on a button and made a change, it has actually spat out the Python command to do that, right? So the first thing that we did was change the inlet velocity and set it to 10. This is telling us exactly what Python command is required to do that. So if you're trying to write a PyFluent script and you don't know where to start, this is a really good place to start. Fire up the web UI, make the changes you want to make, copy the code that it spits out and put it in your script. Really good place to start. I'll close that one now. And just before we hop back into the, no, I'm going to leave that open actually. But just before we hop back into the slides, let's see how our VOF case went. So it's run for 100 time steps. So that's a total of 1 second. And what have we got? We can see that convergence has been really quite good. I've only got one of my, here we go. So yeah, we've got our two animations here. We can see there's obviously a lot of water coming up the front of the boat. It's about to spill over the top. And at the back, we're getting these really cool waves forming. We should actually be able to view these as animations. And there's only 20 frames. I'm not going to see a huge amount, but I mean, the fact that we've just solved 4 million cell mesh for 1 second of flow time on a laptop in like 10 minutes blew my mind when I first ran this case. So there you go, that's sort of running a little bit slowly for this one. Yeah, if we were to run that further, we'd get the full videos that we showed earlier. I think that ran for 20 seconds. It took about 4 hours or so to get 20 seconds of flow time. Alrighty, back into the slides. So this is now into like pre-processing meshing rather than solver meshing. A few new features. So there's now a thin volume meshing feature in watertight meshing. Really, really good for doing anything that involves like stacked plates or like, again, thin layers, something that you're like a bit borderline between using shell elements for or putting a mesh through. So this essentially just lets you use prism layers through thin elements. So it's kind of just like the same as a boundary layer, right? It's not a perfectly structured mesh. It's not a hex cell. It's still like a poly-based cell on the surface, but it just stacks up prisms through those thin regions rather than having like full 3D polys in there. It's much more efficient. A really good example of it is for something like an electrolyzer where we've got all of these thin regions. I know we were just discussing that you can actually not mesh some of these now, but if you do want to mesh them all, this is a really great technique for doing it because you get this like semi-structured mesh using all these prism layers. It's a lot faster than decomposing the geometry fully and doing a full hex mesh in like mechanical meshing or something like that. We can now support multiple periodicity. Previously, if you've tried to make a periodic boundary in Fluent meshing, you could only have like one plane of periodicity. So now there's the support to be able to have, one there is at 10 degrees and the other's at 20 degrees. Really, really handy, again, for like turbo machinery type cases. There's like this automatic extrusion as well for periodics. So we've got like two manifolds here rather than, again, like meshing through them with ugly polys. We can sort of extrude their faces on the periodic boundaries through to each other and get this sort of nice semi-structured mesh between them. Onto invalid normals. So what I mean by an invalid normal is if you have like two surfaces that kind of meet each other like this, you get a region here that's impossible to get a boundary layer forming. So you have to treat that somehow. The default treatment there is to sort of put a sphere at the interface, and it sort of lets boundary layers grow onto the sphere and sort of wrap around that awkward corner. It's a really good technique, but it is quite slow. So if you've got a huge case, you might be sitting there for quite a long time waiting for that to occur. So there's now a new treatment for that just sort of does some smoothing instead. It just kind of bullies the interface into being smooth on at least sort of one of the angles so that it maintains a normal through there. It gets good mesh quality, not great mesh quality, but it prevents all of your boundary layer cells stair stepping down into nothing, which is what we're trying to avoid. We've got the prime wrapper actually, or prime meshing, that again sort of comes from the mechanical world. I think Luke was showing some of its features before. We're now starting to get some of that into Fluent. So for fault tolerant meshing, we've got a new wrapper based on prime meshing, and it's about 3 to 4 times faster. So definitely worth checking out if you're using fault tolerant meshing. We now finally have 2D meshing in Fluent, so you don't have to go out to mechanical meshing for that either. Although I will say if you're doing a more complicated geometry, probably still best to use a mechanical mesher for 2D, but we do at least have one in here now in Fluent. And one last thing on meshing is topology-based workflow. So what I mean by this is you can refine your mesh, again, kind of at leading and trailing edges is where this really is quite important. So external error or turbo machinery type problems. Typically, if you use an unstructured mesh on a leading edge of a blade, you still end up with, like all of the surface cells still want to have an aspect ratio of around 1, right? You can't have an isotropic mesh with your sort of standard unstructured meshing algorithm. So what topology-based meshing does is you can tell it, like, hey, this region here is my leading edge, and I want you to put an anisotropic mesh there. So you can get the correct curvature. You can have nice fine mesh around the curvature, but still have like fairly fat cells going along the leading edge. So kind of something that you usually wouldn't be able to do unless you're doing a proper structured mesh and spending all of the time decomposing the geometry. You now get some of those features for free using this topology-based meshing.